All right, example 3. Doing a Laplace transformation with t to the n. And the reason why I'm doing this is to show you what it's going to converge to. And so we're going to start off again. We're not going to be able to actually find the exact answer, but this is going to lead me to a rule. So I'm going to plug it into my integral, multiply t to the n times e to negative st. And then once again, I got to do integration by parts. So I have u is equal to tn, and dv is e to negative st. Integrate that, I get negative 1 over s, e to negative st. Take the derivative of this, I get n times t to the n minus 1. So now, go ahead and write it out. U times v, negative t to the n over s, e to negative st. And I'm going to take that from 0 to infinity, plus n over s, so multiply v times du, so I'm just going to have the n over s, it's plus again because that's minus. So I just pull that out, and then I have e to negative st, t to the n minus 1. Now, if you notice from last example too, if I plug in infinity there, this part's going to be 0. When I plug in 0 for t, this part's going to be 0. So all of this is just 0. Plus, I integrate e to negative st, t to the n minus 1. When I integrate this, I'm going to have to do integration by parts once again. So I do integration by parts, where t to the n minus 1 is my u, e to negative st dt is my dv. I've already done this before, and take the derivative of that. It's n minus 1 times t to the n minus 2. And so now, when I plug this in, u times v, so there's u times v, which is negative t to the n minus 1 times e to negative st over s, 0 to infinity. I pull the n, this n and the s comes from right here, because I'm multiplying that whole integral. When I evaluate this, I notice I'm going to get 0 again, because I have an exponent to infinity, and it's going to negative infinity, so it converges to 0. And I plug in 0 for t, that's going to give me 0. So the same thing happened once again. And now I'm going to pull out a n minus 1 times s, do that over here, n minus 1 s, again plus because that's minus. The integral from 0 to infinity, e to negative st times 10 to the n minus 2. And I notice a pattern that emerges. The integral is just the same thing as it was previously, except for instead of n, it's n minus 1 over s. Instead of t to the n minus 1, it's t to the n minus 2. And so since I notice that there's a pattern that emerges, when I clean this up, I get n times n minus 1 over s squared times the integral from 0 to infinity, e to negative st, 10 to the n minus t to the n minus 2 dt. If I did it again, I would get e to the negative st times 10 to the n minus 3, and I'm going to be multiplying this by n minus 2 over s cubed. And so because there's a pattern, I'm able to denote a general solution anytime I have my t to a power. And so my n is going to be whatever my exponent is, and anytime I have to do the Laplace transformation to t to the n, I just take the factorial of the power and I divide that by s to the plus 1 of whatever power that we have. Alright, and this is going to pop up on the top of the next sheet. Now, so here's my answer. Here's my Laplace transform. So I could say that that is my f of s. Alright, so now example 4, I'm going to do a Laplace transformation with trigonometry. Here we have sine of kt, where k is going to be a constant. And so we're going to do a Laplace transformation of that. So I put it in my integral, multiply by e to negative st. And here I notice I have trigonometry and I have an exponential. So what I'm going to do is I'm going to do tabular method. I could do integration by parts. I'd have to do it a few times. Or, I call it the tic-tac-toe method, where we just go ahead and label this as e to the negative st, and this is sine k of t. I take the derivative of the left side, and I take the integral of I do integration to the right side. So the derivative of sine is cosine, so I got k cosine kt. Derivative of cosine is negative sine, so negative k squared sine kt. So there's all the integration. This is all of the integration. So when I integrate e to the negative st, I get negative 1 over s e to the negative st. And then I do it one more time, and I get 1 over s squared e to the negative st. Now, the reason why I stop here is because I'm going to get back to an integral that's going to look very similar to the original integral which I started with. And so I go ahead, and when I show my tabular method, it's going to be sine of kt times e to negative st is what I have, I'm sorry. And so from right here, so when I take the integration, you go ahead and you go diagonal. So it's going to be sine of kt times negative 1 over s e to negative sine of t. So that's what I have here. And then minus k cosine kt times 1 over s squared e to negative st, which I have right here. Now, because I don't have another diagonal to go, I keep this the same, but this is going to be an integral. So I get negative k squared over s squared times sine of k e to negative sine t, all that under the integration. So because this is not under integration, we went ahead and were able to integrate this. I'm going to evaluate this from 0 to infinity. All right, but this part over here, all right, the part that's the integral, what I'm going to do is I want to get rid of this. And I noticed that, oh, hey, this is the same thing that's on the left side. That's why we stopped after we did, 2 steps of this. And we're going to bring it to the left-hand side. In order to do that, I got to add k squared over s squared. And what's going to happen is the right side's going to eliminate, and I'm going to bring it over here. And when I add it, notice that I have an s squared as the denominator. So this is really s squared over s squared to give me 1. And when I add s squared plus k squared, I get s squared plus k squared all over the same denominator of the integral e to negative st sine of k dt. Now, when I go ahead and substitute in here I have infinity and 0 for my integral. I plug in infinity first. This gives me 0 for the first part. Plug in infinity here. I get 0 once more, so that goes away. Then I plug in 0. If I plug in 0 to sine of kt, it's sine of 0, 0, so that goes away. So the only thing I really am left with is when I plug in 0 in for this t. This is going to give me 1. Cosine of 0 is 1, so it's really negative k over s squared. But since I subtract this because it's the second part of the integration, it's really plus k over s squared. And so now the left-hand side equals the right-hand side. But what I want to find is the integral from 0 to infinity, e to negative s sine of t times sine of, it should be kt d of t. And when I do this, I'm going to get, what I'm going to do is I'm going to have to divide that to both sides. So I'm going to multiply s squared over s squared plus k squared. When I do that, the s squareds are going to cancel out, so I'll show the multiplication. I'm going to multiply by s squared over k squared plus s squared. And that's going to cancel that out, and so I'm left with k in the numerator, s squared plus k squared in the denominator. And again, this is my Laplace transform.